Good morning student, myself Millie Sankla, and today's session we continue with our subject design of prestressed concrete structure, and today we solve the example of composite section. Okay, now this one is the design of composite section. In for previous session we analysis the composite section, and today we design composite section, and here we take an example of beam. Now first step, find out z dash b, that is greater or equal to zb m dash divided by zb eta fct minus ftw minus m minus eta m minimum. This one is the equation of find out z dash b. Now we understand the full form of each term. First one is the what is z dash b. Z dash b is equal to section modulus of bottom fiber of composite section. Okay, in composite section top fiber is subjected to cast in situ and bottom fiber is subjected to precast time, and this one is the section modulus of bottom fiber. M is equal to moment acting on precast part of composite section during the construction. M dash is equal to moment acting on composite section which is generally due to the imposed load, or we can say live load. Okay, simply M is equal to moment due to precast section and M dash is the moment acting on composite section. Okay, and this one is due to the live load. Now eta is equal to loss ratio. ZB is equal to section modulus of precast unit. Okay, this ZB is the section modulus of precast unit. Okay, FCT is equal to compressive strength in tensile zone, that is 0.5 FCI. And what is FCI? FCI is the compressive stress at transfer. Okay, this one is the compressive strength of concrete at transfer stage. And FTW is the tensile strength of web, and this one is the -1 Newton per mm square. M minimum is the minimum moment, and that is 0 for prop construction. Okay, now we find out bottom and top fiber precast prestressed beam. Okay, here we find out prestress of top and bottom fiber. First one is the INF, that is greater or equal to FTW divided by eta plus M divided by eta ZB plus M dash eta Z dash B. Now we find out F supportive, that is at bottom fiber, greater or equal to FTT minus M minimum, that means minimum moment, divided by ZT. Okay, now according to this equation we solve the example of composite section with design. Okay, now first one, read the data. Design a composite slab for bridge deck using standard inverted T-section. The top flange is 250 mm width and 100 mm thick. The bottom flange is 50 mm width and 250 mm thick. The web thickness is 100 mm and the overall depth of inverted T-section is 655 mm. The bridge deck has to be supported. A characteristic imposed load is, that is 50 kN per meter square. Overall and effective span of 12 meter. Grade of concrete for precast pre-tension T is M40 and compressive transfer is 36 Newton per mm square. For cast in situ concrete, the grade is M30. Determine the minimum stresses necessary and check for safely under the limit state of serviceability. Okay, here we use a limit state method. This one is the section. Okay, inverted T section. Now total depth in data, total depth of this section is given, that is 750. Okay, overall T section is given, overall this girder is given 655, and this 95 is given cast in situ, that means cast at place, and 655 is for precast time. Now we first of all will find out properties of inverted T section. This one is the inverted T section, or we can say I girder. Now area, first of all the area of top flange 250 into 100, second is 100 into 305 web, and bottom flange 250 into 500, and answer is 1,80,500 mm square. Now we find out YB from bottom. Okay, and that is A1 Y1 plus A2 Y2 plus A3 Y3 divided by A1 plus A2 plus A3, summation of total area. Now A1, that means 250 into 100 from bottom fiber, here 605 Okay, then web 100 into 305. Okay, and from bottom 250, then 305 by 2, and third one 500 into 250 and 250 by 2, and answer is 221 mm. Okay, here we find out bottom fiber. Now we find out top fiber. Then YT is equal to total depth, that is 655, minus YB that we recently find out 221, and answer is 434 mm. Now we find out moment of inertia of this girder, and that is according to our parallel axis theorem, Ig plus A square. Put the all values in this equation, and we find out moment of inertia of total section, that is 6.75 10 raised to 9 mm raised to 4. From this moment of inertia, next we find out section modulus of top fiber and section modulus of bottom fiber. Now first we find out ZT. ZT is equal to I by YT. I means moment of inertia of total section, and YT, that means centered of top fiber from CGC level. Okay, and that is 434. Answer is 15.55 into 10 raised to 6 mm cube. Then we find out section modulus at bottom fiber, that is equal to I by YB. I is equal to moment of inertia of this overall section, and YB is equal to centroid from CGC level, bottom centroid, that is 221. 30.54 into 10 raised to 6 mm cube. Now next, here eta is given 0.80 because 20% losses are given, so our efficiency is 0.80. The minimum moment for propped construction is 0. We consider as 0. Now we find out self weight of this precast beam and cast in situ concrete. So here we consider total section. Maximum width is given 500, so 0.5 meter. Then overall depth of this precast and cast in situ, that is 750, so 0.75, and 24 is the density of concrete, so 9 kilonewton per meter, that is the self weight of this total section. Okay, now next we find out bending moment M. Bending moment M is equal to WL square by 8. W we recently find out, that is our self weight 9. Span of this beam is given, that is 12 square by 8, 162 kilonewton into meter. Now we find out live load. Live load is equal to 50 into 0.5. Okay, that is 25 kilonewton per meter. And again we find out moment due to live load, that is M dash, that we use in equation. M dash is equal to moment due to live load, or we can say imposed load, WL square by 8. W 25. Okay, that is 450 kilonewton into meter. Now FCI is given in data, that is 36. FCT already we know that is 0.5 FCI. Okay, 0.5 into 36, answer is 18 Newton per mm square, and this is the permissible compressive stress. Now the permissible tensile stress in concrete under service load. Now we find out permissible tensile stress under service load, that is FTW is equal to -1 Newton per mm square, and FTT, that is -1 Newton per mm square. Okay, at transfer, and that is under the service load. This is given in our data. Now we find out section modulus of composite section. Okay, that we already know in theory portion, that is Z dash B. Now what is the equation of Z dash B? Z dash B is equal to ZB into M dash, ZB eta FCT minus FTW minus M minus eta, then minimum moment. Now one by one put the value. ZB is equal to our section modulus 30.54 into 10 to the 6. M dash is equal to moment due to live load, that is 450. ZB again bottom fiber section modulus 30.54 10 to the 6. Eta 0.8. FCT is equal to 18. Okay, this one FCT is equal to compressive stress. Okay, that is 18 plus second minus FTW. FTW is equal to -1, so minus minus plus. M is equal to our moment. Okay, that is moment due to self weight of composite section, 162 into 10 to the 6, and minimum moment is equal to 0. So 0.80 into 0 is equal to 0. Ultimately our section modulus ZSB is 44.57 into 10 raised to 6. This one is the section modulus for overall composite section. Okay, now next, here H is the total depth of composite slab. Okay, and section modulus of this section is BH cube by 6, and here we find out 44.54 10 raised to 6. Okay, this one is the our new section modulus for our composite section. Okay, so put the value 44.57.10 and the actual equation of section modulus is BH square by 6, or we can say BD square by 6. Okay, here H is equal to D. Now B is equal to maximum width, that is 500, H square by 6, and 44.57 into 10 to 6. Here value of H we find out 731.32 mm, that this is the required depth or height of our section. Now total depth 750 mm provided as advocate. Here we provided, okay, in this section we provided, look at this, in section we provided 750 mm, okay, and our actual required depth we find 731.32 mm. Okay, now we find out stresses at top and bottom fiber. Now F, this one is the top stresses, FTW divided by eta plus M divided by eta ZB plus M dash divided by eta Z dash B. Okay, and Z dash B is equal to BD square by 6, that is 46.87 into 10 to 6 mm cube. Okay, now next put the value, and answer is 17.38 Newton per mm square. Next we find out bottom stresses, that is F T minus minimum moment divided by ZT. Okay, and this FTT is equal to -1, and this one is 0. So stresses at bottom is equal to -1 Newton per mm square. Okay, now we find out minimum prestressing force P. P is equal to A, then stress at top fiber into ZB plus stress at bottom fiber into ZT, ZT plus ZB. Okay, put the all values in this equation, and our prestressing force P is equal to 2017 kilonewton. Okay, lastly we find out eccentricity E. Eccentricity E is equal to ZT, ZB, then F INF, that means top stresses, bottom stresses. Okay, A, then top fiber stresses into ZB, bottom fiber stresses into ZT. Then again put the all values in this equation, and our eccentricity E is equal to 93.85 mm. Now here according to our eccentricity we provide reinforcement in our composite section. Okay, main purpose is find out eccentricity, and then according to eccentricity we provide reinforcement vertical and horizontal bar in our composite section. Okay, next example, highway bridge deck slab spanning 12 meter is to be designed as a one-way slab prestressing concrete slab with parallel post tension cable carrying a effective force of 650 kilonewton, that means that is PE. Deck slab is required to support a uniformly distributed load 20 kilonewton per meter square. Okay, and the permissible stress in concrete should not exceed 16 kilonewton per mm square. In compression, no tension is permitted at any stage, that means all tensile stresses is 0 here. Design the spacing of cable and position at mid-span section as a loss of pre-stress is 20%. Okay, here we design for one-way slab. Now first of all mention the given data. First one is span of this one-way slab L is given 12 meter and working live load is given 20 kilonewton per meter square. Okay, and prestressing force in cable is given 650 kilonewton. Here the uniformly distributed load is given 20 kilonewton per meter square, and this will be act as a live load on our slab. Permissible compressive stress in concrete as a FCT that is 16 Newton per mm square. Okay, here next we find out permissible tensile stresses, that is given 0 FTW and FTT. Okay, loss ratio is given 20%, so 100 minus 20 is equal to 80%, so efficiency is eta is equal to 0.80. Now here we consider that 1 meter width of slab, so here we take B is equal to 1 meter and live load on slab is equal to Q, that is equal to 1, that is width, okay, into 20, so kilonewton, 20 kilonewton per meter, that is the live load of 1 meter width. Now live load moment, here we find out live load moment, that is W L square by 8. W is the live load, that is 20. Spanning of this beam slab is given 12, so 12 square by 8, that is 360 kilonewton into meter. This one is the live load moment. Now H is the overall depth of slab and B is equal to width of slab. Mg is equal to moment due to self-weight of this slab. Here self-weight of slab per running meter is B into H into density of concrete that we use for construction of slab, and this one is the unit conversion 10⁶. Now here we put B into H into 24 10⁶, and span W L square by 8. W is the self weight and L is equal to W 12 square by 8. After simplification, answer is 432 BH. B and H, B is equal to 1000, that we already assumed, and here we find out height of slab. Okay, now the range of stresses at bottom fiber equation is FBR is equal to eta FCT minus FTW. Okay, eta 0.8, FCT is given in data, that is 16. Okay, compressive stresses, FTW, that is our tensile stresses, that is 0. Answer is 12.8 Newton per mm square. Now relation is ZB greater or equal to BH square by 6 greater MQ plus 1 minus eta mg FBR. Okay, that is our bottom fiber stresses. Now here we equate, because if we want to find out the values we can't take greater than, if we compare the value with equal to, so BH square by 6 MQ, that is the moment due to live load, 316 to 10⁶, plus 1 minus 0.8 432. Okay, this one is 432 mg. B is equal to 1000, H is unknown, and divide by 12.8. 12.8, that means our bottom fiber stresses. After solving that, here we find out H is equal to 431.53 and we assume as a 435 mm, and area of this slab is equal to width is given 1 meter 1000 into 435 mm, that is 4,35,000 mm square. Now we find out ZB and ZT, that is BH square by 6. B we recently find out, okay, and H is equal to 435 divided by 6, that is 31.53 10⁶. Now we find out moment due to self-weight, that is 432 into B into H. B is equal to 1000, H is equal to 435. Then moment due to the self-weight or dead load is equal to 187.92 into 10⁶ Newton into mm. Now we find out stresses at top fiber and stresses at bottom fiber. Now at top fiber, FTT minus mg divided by eta into ZT. Now tensile stresses here 0, then mg is equal to moment due to dead load, that is 187.92 into 10⁶ divided by eta. Eta is equal to 0.8 and ZT is equal to section modulus of top fiber. Answer is minus 7.45 Newton into Newton per mm square. Okay, now here we find out stresses at bottom fiber, that is FTW, then eta plus MQ plus MG divided by eta ZB. Okay, after simplify we get answer, that is 21.72 Newton per mm square. Okay, this one is the Newton per mm square. Same here stress is Newton per mm square. Okay, now next we find out, here Prestressing force P is equal to A by 2 FB plus FT. Okay, stresses at top fiber and stresses at bottom fiber. After that, our prestressing force is 3104 kilonewton. Then we find out eccentricity for our slab. Section modulus divided by area. Then difference between bottom stress minus top stresses and summation of bottom stress plus top stresses. After solving that, eccentricity we get 148.16 mm. Now we find out spacing to provide a cable to maintain this eccentricity. Spacing of cable is equal to 650, that one is the prestressing force. Kilonewton is given, so 650 into 1000 and divide by our 3104. This one is the minimum prestressing force required. Okay, so spacing is 209.40 mm. That means here we adopt a round figure, that is 200 mm center to center for cable in direction of span. Okay, here we find out spacing for cable that we provided in our slab. Okay, just now we stop here. In next session we start with our new model. Okay.